You're here because you want to master carbonyl compounds with a University of Cambridge graduate. Let's begin. In this video, I will be going through with you what are the reactions of carbonyl compounds, as well as a new mechanism called nucleophilic addition that carbonyl compounds go through, and some of the reasonings behind why reactions work a certain way. And lastly, some of the distinguishing tests that are very unique to carbonyl compounds. Carbonyl compounds are mainly distinguished by this very distinguishable C double bond O group. Now in this masterclass, I'll be going through two kinds of carbonyl compounds. One is aldehydes, for example ethanol over here, and the other one is ketones, which is distinguished by the same C double bond O but with two R groups attached to the side. Some of your other common aldehydes that you probably would need to know are like benzaldehyde, which is a very unique name, and for naming purposes, when there are multiple aldehyde groups in the same organic compound, propane diol. Take note of the di in front of the L, which stands for two aldehyde groups within the same organic compound. Now, how do we prepare our carbonyl compounds? We can either oxidize primary alcohols to turn them into aldehydes. So you can refer to my hydroxy compound masterclass, where I run through the reagents and conditions, as well as the mechanisms for these kind of reactions as well. You can also oxidize secondary alcohols into ketones, and there you can also refer to my hydroxy compound masterclass. As for reactions of carbonyl compounds, you can oxidize your aldehyde into carboxylic acids. We briefly ran through this in hydroxy compounds, but this is just for you to take note that when aldehydes further undergo oxidation, they can turn into carboxylic acids, such as the one over here. Now the reagents and conditions are very similar to your typical oxidizing reactions, where you use either potassium dichromate 6 or you use potassium manganate 7 in acidic or alkali conditions, depending on which is preferred. Generally, it's preferred to have acidic conditions, and you must heat. If you use dichromate 6, it will turn from orange to green. And if you use manganate 7, it will turn from purple to colorless. Take note that ketones cannot be oxidized. Do note this. Your carbonyl compounds can be reduced as well. Your aldehydes can be reduced to primary alcohols, and your ketones can be reduced to secondary alcohols. Do refer to my hydroxy compounds masterclass because I run through the reagents and conditions there as well. Next, I want to quickly look at this table. This table briefly tells us the different functional groups that can be reduced, as well as whether it can or can be reduced by the different reducing agents. Some of the common reducing agents we've gone through so far are like your hydrogen gas with nickel catalyst, your lithium aluminium hydride in dry ether, or your sodium borohydride in ethanol. Now, do take note very cleanly that your alkenes and your alkynes, basically your C double bond Cs and your C triple bond Cs, cannot be reduced by lithium aluminium hydride and your sodium borohydride. And this is because both your lithium aluminium hydride and your sodium borohydride provide H- ions. And these H- ions usually do nucleophilic attack on a C double bond O, or something that is electron deficient, like this or like this, for example. And because alkenes or alkynes are not really electron deficient, they don't fall into that category, and hence they can only be reduced by hydrogen gas. You will realize that your carboxylic acids, which is this, your esters and your amides, can't really be reduced by sodium borohydride. And this is mainly because lithium aluminium hydride is a stronger reducing agent than your sodium borohydride. So I've stated over here down below as well that both your lithium aluminium hydride and sodium borohydride again provide H- nucleophile, so they cannot really attack the C double bond C and C triple bond C. And your lithium aluminium hydride can reduce your carboxylic acids, your esters, and your amides, but your sodium borohydride cannot. It's because lithium aluminium hydride is a stronger reducing agent. And the explanation for this is that aluminium is more electropositive than your boron. Therefore, you have a greater delta minus on the H for aluminium hydride compared to borohydride. Therefore, it is just a stronger reducing agent when you have a H that has a stronger delta minus. Next, I want to introduce a new mechanism, nucleophilic addition. This is a special mechanism that your carbonyl compounds can go through. So what starts us off is that because your carbonyl compounds, the C is electron deficient because it's bonded to the electronegative O, you need to write your delta minus and your delta plus as such. And this is what propels the reaction. Your nucleophile is going to hunt for the electron deficient carbon and attack it. And take note that this is a slow step. And that's how your nucleophile will attach itself to the carbonyl carbon. Then, your O minus over here is going to take a hydrogen from a little Bronsted-Lowry acid or proton donor that is inside the solution as well. And because of this, delta plus and delta minus, it enhances the reaction as well. Therefore, this second reaction is also a fast reaction, and that's how your nucleophile is going to be added across the C double bond O. Do take note that your rate is equals to K times the concentration of your carbonyl times the concentration of your nucleophile, because both your carbonyl and your nucleophile are involved in the slow step of your reaction. A little recap in reaction kinetics. Also, your HA, as I've said just now, is your Bronsted-Lowry acid, or in other words, a proton donor. Do also take note that a racemic mixture can be produced when the C in your C double bond O becomes a chiral carbon in the final product. And this is mainly because there's equal probability of the nucleophile attacking either side of the trigonal planar carbon in C double bond O. So you do realize that this is a very common theme when it comes to trigonal planar carbons and it getting attacked by a certain compound either from the top or either from the bottom of the plane. And therefore, because of this 50-50 chance, right, your enantiomers will be formed in a 50-50 ratio, aka a racemic mixture. Do also take note that your aldehydes undergo nucleophilic addition faster than your ketones. And this is mainly because the carbon in the C double bond O for your aldehydes are more electron deficient than the carbon in ketones. And this is also because your ketones have more electron donating R groups than the aldehyde to the electron deficient carbon. And therefore, it doesn't really undergo nucleophilic attack as much for your ketones. Also, your ketones has more bulky R groups, and therefore it sterically hinders the approach of your nucleophiles as well. So a typical nucleophilic addition reaction that you will need to know is the nucleophilic addition with HCN. Now the reagents and conditions are HCN with trace NaCN or NaOH and in cold temperatures. The nucleophile here is Cn minus, and the Bronsted-Lowry acid is HCN. Now why is it in cold temperatures? This is mainly because you have to prevent poisonous HCN gas from escaping to the environment. If it's too hot, the gases will get very fizzy and very rowdy and just escape. Now what are some of the distinguishing tests for your carbonyl compounds? There's condensation with 2,4-DNPH, and you have to memorize the structure of 2,4-DNPH. You need to know how to draw it. DNPH stands for dinitrophenylhydrazine. And this is a condensation reaction because, as you can see in this boxed up part over here, H2O actually comes up as a byproduct in this reaction. And the reagents and conditions for this distinguishing test are 2,4-DNPH, to memorize the name as well, at room temperature. And why this is such a good distinguishing test for your carbonyl compounds is because it produces a very distinguishing orange PPT if the carbonyl is present. Next, you can also do a silver mirror test with Toland's reagent. This is an oxidation reaction. And what's going to happen is that your aldehyde, right, the R group can be an alkyl group or a phenyl group, and this will produce a carboxylate salt with your silver solid, which is the silver mirror, hence the silver mirror test. And the reagent conditions are Toland's reagent, so do memorize the reagent as well. This is the complex that's being used under heat. And the observation is you'll produce a silver mirror or sometimes just a gray/black PPT, which is just a silver solid. The balance equation is also something that you should try to memorize if you can, because this will save you some time during the exams as well. Next distinguishing test is failing solution. This is also an oxidation reaction, and what's going to happen is almost the same thing. Your aldehyde, this time the R group has to be an alkyl group, not a phenyl, right? It turns into a carboxylate salt and produces this brick red BPT, which is Cu2O solid over here. And the reagents and conditions are you have to add failing solution. This time you don't really need to memorize what the solution formula is. and then you just heat it. But just know that filling solution is this alkaline CO2 plus complex. Now as for the balance equation, again, I will encourage you to memorize it so that you can save time during the exam as well. Lastly, your carbonyl compounds in this specific orientation, specifically this C-double-bond-O CH3 group that is boxed up, can undergo this iodoform test. Now this iodoform test will produce this carboxylate salt as well, along with this CHI3, which is very distinguishing because this produces a pale yellow PPT over here. You will also get brown I2 that decolorizes because that is part of your reagents. Your reagents and conditions are the I2 in NaOH aqueous under heat. And as for the balance equation, I will also highly encourage that you go and memorize this. So that's all for carbonyl compounds. I will highly encourage that after the lessons, you go and memorize some of the key aspects of carbonyl compounds, such as the reagents and conditions, as well as the reaction mechanism, along with the reasoning behind why the mechanism works as such as why does nucleophilic addition give a racemic mixture. Then I will encourage you to do some practice. Practice drawing the mechanism, practice answering some questions related to carbonyl compounds. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. If you would like to subscribe to my online class, be sure to hit the link below so that you can book a free call with me, and I can run through with you your past papers as well as any doubts and clarifications you may have, and show you why my class is the best fit for you. I'll see you in the next lesson.